Well, so I sent an email around on Friday, I think, or I guess Thursday, I think. Actually, not Friday. So you know it's from sections 8, 9, 10, and 11.1. So 11.1 is really just type 1 pipe flow problems. So that was the original word. And then the second word is that there are really two questions. One long question on dimensional analysis, Buckingham Pi. And so that is to, the recipe of getting the dimensional variables, the pi groups, and then what do you do with them, basically. So we've done that in class with a couple of things. And the other one is an energy equation, pipe flow equation. They're the same thing. So what we did in week 8, what you did in week 8 in this particular year, is the energy equation, which includes the viscous losses attached to Bernoulli equation. So it's just Bernoulli equation plus an ability to be able to count for viscous losses, these losses in pipes and losses in fittings, HL, major and minor, and also to put pump energy into the system as well. And so what I thought today is we'll just go through all the materials that we have. They are the same materials that are online from last year. I didn't change them. I won't. There's no need to change them. I think it summarizes the things that we need well enough. And so that's the plan for today. I don't know if you have any questions from me before we get rolling on that, which I'm happy. Yeah, go ahead, shout.
Does that mean that we're not going to be doing like this sports media and
Not necessarily, because force media is actually the energy equation where the viscous losses are included in it. But you might put that on the sidelines. Maybe that will come on the final. I think there's one on the final last year for that. And so, yeah. So you can draw whatever conclusions you wish from that. Any other questions? It's good to have these cameos on the thing, right? So you'll be able to sense a mood. All right. So so those are the main areas. So Buckingham Pi dimensional analysis and the energy equation. The energy equation comes in two forms. We derived it by Reynolds transport theorem, but I'm not sure we have to really go back all the way to do that. But it comes in these two flavors, if you like. One flavor that's quite familiar to us, written for some reason backwards here. Remember upstream and remember downstream. So these are the ones that we've used before. What else do we know? So pressure head, velocity head, elevation head. We've always said that these modifiers, these alpha coefficients, are basically equal to 1. It just accounts for the distribution of flow across a pipe, for instance, or in the stream tube, which of course pipe flow would be within the stream tube. These are the losses that we've dealt with for pipe losses, major losses, incrementally small but large over the length of the pipe. And we know that HL, we'll see this again for sure, is equal to what? Friction factor, length over diameter, and V squared over 2G, the velocity head term. This is in the pipe. And HL minor, which are typically some loss coefficient, which is a constant. We assume basically that it's turbulent flow, fully developed turbulent flow, and so it's just a straight number. Somewhere between 0 and 210, I guess, was the largest one we found. And again, multiplied through by the velocity head. Again, this is the velocity in the pipe or in the fitting, rather than at the nozzles at each end. So just be aware of that. So upstream, written different from what we usually do it. This would be 1, right? Subscript 1. This would be subscript 2 in our case. And the pump heads, I suppose, important to know that because we've used it, is what? It's equal to the power We've sometimes called it W. We've sometimes called it P for power, divided by acceleration due to gravity and the mass flow rate. So mass flow rate is just volumetric flow rate times density. So we've been moderately consistent in our units. I think we've also used the fact that sometimes interchangeably in your notes you'll see that mass flow rate is referred to as lowercase m. There's no distinction as far as I'm concerned. We've used them both kind of interchangeably. And so that's the energy equation. So it's the only way in which it differs, of course, from Bernoulli is that it has a loss term for viscous losses, including porous media flows, which, yeah, and also allowing us to put energy into the system or to take energy out of the system. HP is positive if you're putting energy in as a pump, and negative if it would turn out to be negative if you're taking it out as a turbine. Mass flow rate is always a scalar, positive, right? So it's not directional, going across a boundary as we dealt with in Reynolds transport theorem, because this is the streamline equation. So I haven't drawn it here, but of course you know it's this. Whoops, sorry. This is HP, and this is across the system, and what else? Yeah, that's fine. So I guess mass flow rate is just the amount going out. Since it's closed, it has to be the same amount coming out the other side typically as well. Yeah, I guess, yeah. Yes, shout. Well, yeah, okay, yeah, it depends. If it's just mass flow rate, then it's Q rho. If it's the whole denominator, then it's Q gamma. Yeah, yeah, good.
Derek,
Yeah.
what's the physical difference between a major and a minor loss?
Nothing, just the way we classify them. Major loss is a euphemism, I guess, for the loss in the pipe. Incrementally, it's very small, but when you sum it up over the length of a pipe, it's usually more than the loss in a single fitting. And the minor losses are the ones that are in the fittings, almost always assumed in the stuff that we've done that they're turbulent. So I guess that's the one main difference. So that they're difference in magnitude because the minor losses are typically smaller. It's a large loss in an individual fitting compared to a small loss per unit length of the pipe, but over a long length of pipe. But I suppose the real difference is that minor losses are always, we assume that they're turbulent. Because this KL value is just given as a constant independent of Reynolds number. And so if you look at the Moody charts, for instance, which we'll get to soon enough, this is Reynolds number versus friction factor. Then we have, this is these three different regimes that are split around 2,000 and 4,000. Then we end up with these portions here. These are pipe losses which are a function of relative roughness. So this is rough, this is smooth. But the point is, I guess, that I'm trying to make, this is horizontal. And so friction factor is constant for these. So the assumption for these, not assumption, the reality for these is that they're turbulent. And the outcome of being turbulent is that the friction factor doesn't change. It's constant, just by observation. Answer? Probably more than you wanted, but anyway. Okay, and so that's one way we've seen this energy equation. The other way is a little different, and we've used it less, but we've used it nonetheless. These are the same expressions down here that we talked about at the bottom. This is the same as this, uppercase M. So that's no different. But this is the energy equation, again, written between point number 2 and point number 1, upstream and downstream, as we've done it. Again, elevation head, It's not head anymore, right? It's g times different units. So I guess it's in meters per second squared. So this is in meters squared second squared, each of these terms. Obviously, velocity is length over time, so it's meters squared, length squared. So it's length squared, time squared, over time squared when you look at squaring it. And this is enthalpy, right? And enthalpy from your thermo is equal to both internal energy plus pressure energy. So really potential, right? Compress air in a tire, you let it out, it's got some stored energy attached to it. And so again, this has to be in units of length squared over time squared, which is really a euphemism. One of your homework questions was a mass rate in newtons per second or something, right? Because it was hidden with gravity was in there in the past homework assignment. So I think this is joules per kilogram. It's basically internal energy is really what the units are. But it turns out if you multiply that out, knowing that a joule is a newton meter, newton is the force needed to accelerate a kilogram by 1 meter per second squared. So you can work the units out in this. This is mass rate. So this is kilograms per second, and it's not. It's a scalar value, single magnitude. So it's not different as to whether it's going in or out, like it was in the representation of the Reynolds transport theorem, but it's just a straight scalar value. Yeah. Sorry? Yes, and yeah, we used them both, yeah. For both those conservation equations, we had to take care of the signs going in. This is the heat that is put into the system, and this is the work which is put into the system. They're positive if they're in, so this would be positive in other words, if it's a pump, and it's negative if you're taking energy out, as in a turbine, converting energy. This would be positive if you're putting in energy, negative if you're taking it out, heat energy. And more usually, in the one example that we'll look at in a second, this is 0 if it's adiabatic. Adiabatic means it's isentropic. No energy comes out of the system. The energy's stuck in the system. Okay. So that's kind of in a nutshell, I guess, all our stuff on the energy equation. You for sure, and we'll talk about this again, for sure should know how to use this. It's been quite important in what we've been dealing with when we've talked about, bless you, pipe flow. And so, you know, from what I've said about the energy equation, you could probably surmise that there's a question on pipe flow that involves this in some interesting way. Always an interesting way. There's always a message in these questions. I'm not sure whether you appreciate that or whether you don't give a damn, but you probably don't give a damn. Got other things on your mind. But anyway, there's usually a message in these questions. Okay? So I'm going to roll from that. Don't really care about this. This is just a repeat of these. This is enthalpy as a function of internal energy and the potential. This is exactly the same equation as before. Certainly, I wasn't here in person for this, but in the movie, I think in the videos, you'd have seen this. Just a quick example. Looking at transformation of enthalpy as it comes into a system. Enthalpy comes in at some magnitude, goes out at some different magnitude. When you do the balance, this is really an energy balance equation, just like conservation of momentum and conservation of mass, as we've just said. And if you know the amounts going in versus going out, in versus out, in versus out, if you know the velocities in versus out, then you have most of the things that you need to put together in this particular expression. If it's adiabatic, this is 0. And so the only other remaining factor is to figure out what this is in this particular question. We know what the amounts in are. We know what the velocities in and out are. I guess in and out one is upstream. Always remember that. Don't get your upstreams and downstreams mixed up. And I guess the only thing that's different in this is that we don't know W shaft net in an absolute way, but we know it in a relative to the mass flow rate. And so we can get this, if I just scroll this up one page, I think this should have a dot attached to it, right? We can calculate what the power coming out of the system is merely, I guess, by substituting this in here. And so, well, that's the expression that we use all the time. But this is the expression that we can get the shaft work per unit mass flow rate is basically what this is. So this is shaft work per unit mass flow rate. Don't really want to spend that much time on this question actually, but we're stuck in there. And so you can take from that what you will. So anyway, so we can't, for this particular question, we only know it in terms of the flow. We don't know what the mass flow rate is, and so all we can solve is basically for the energy that comes out per mass flow. And so we know all of these terms. We can rearrange this to take this over to the left-hand side by dividing both sides through by mass flow rate, in which case we get this term here on the right-hand side. And since we know this, and this, and this, and this, then we get an amount out of the system which is 797 kilojoules per kilogram of massive hot water that goes through the system. And again, we just have to take care of our sign conventions. Here we've switched signs. If it's net shaft out, it's positive. If it's net shaft in, this is a turbine. Sorry, we want net shaft out, which is a negative of net shaft in. And so it comes out that the amount in this is equal to the net shaft out. So this is the amount of energy we get out of the system by running it through at these two different upstream and downstream energy levels. And so it's just an accounting of the energy in the system and your sign convention, I guess. So don't forget the sign convention. Always the work is positive if you're putting energy into pump. It's negative if you're pulling energy out of the system. Okay. I don't want to spend too much time on that. So this equation comes in two flavors, as we've seen here. This is the flavor we've just used. They're both the same equation. They're just written a bit differently. And this is the one that by far we spent most of our time on. It looks much more like Bernoulli. And so the second example is just doing that. A pump flow problem where you're putting energy into the system to raise stuff from one level to another level. You can write Bernoulli's equation with the energy components in there, head losses. What do we know? Pressure. We know elevations. We know this is before, I guess there is some head loss in the system just from the fittings, which is defined here as this fitting. So the only head loss I think is just this. This is the velocity in the fitting as it goes through. And we want to know how much energy we have to put in the pump. So that's power divided by gravity times mass flow rate. Mass flow rate is equal to density times Q. So circling those just to be clear, this is mass flow rate. Density times cubic meters per second times kilograms per cubic meter gives you mass per kilograms per second. And I think in the twist in this particular case is that the pump head is given as a function of flow rate. And so the pump equation, if you like, defines a pump head as a function of flow rate. This has to be in units of length. All of these are, of course, in units of length, and so we know we have to be dimensionally consistent. It's ancient history for you now. You take care of that all the time. We stress it maybe in the first week, but now, of course, that's kind of natural thing for you to do. So this has to be, this equation is in meters. This would be in meters cubed per second to give you these terms. Oh, sorry, feet. Sorry, it's not metric. This would be in feet of head, and this would be in cubic feet per second. And just rearrange things. What's it asking for? It's asking for, I'll look at the bottom just to see. It's asking what the flow rate is if you're using that. Yeah, what the equilibrium flow rate is in this particular case. I haven't looked at it in particular detail. And so you'll end up with an unknown value of Q in here. I guess you know that, okay, I guess the big tank, to make life easy, the big tank assumption is that these are 0. I'm guessing. And therefore you have an expression which includes the elevation difference, which is 100 feet. It has the pump equation, which is this, and it has some length term, head loss term. They're all a function of velocity. This is a function of velocity. This is a function of a known value. And so you can solve for velocity. If you know velocity, you can solve for flow rate just by multiplying through by the cross-sectional area of the pipe. Okay. So remember that we have the energy equation in two different forms: the enthalpy type form, but more commonly the Bernoulli-esque type form with the viscous loss terms and the ability to put energy into it. But they're identical, right? You see that these terms that we're talking about here, that this pump head term is really just this component here. And of course this doesn't exist in this equation here. So I realize that's a minefield of scroll there. Perhaps it doesn't make sense, but hopefully it does.
Question.
Yeah.
There are no major losses in that problem?
There was one, this one. Oh, no major. Yeah, no major. No. Taken, must be a short pipe. Length is small. So what's the question? Who cares what it's reality? I guess major losses would have been fine, right? So long as they're turbulent, you could solve it in one step. Otherwise, you'd have to solve a Reynolds number. Yeah, let's not spend time on this. Okay, dimensional analysis again. So I'm expecting you to ace this test because, as I say, it's starting to become a bit more formulaic and recipe related. And so you should be able to, you've seen enough of these problems to know what they look like. Dimensional analysis, incredibly powerful technique to be able to define a problem in terms of the controlling variables, fluid variables of density and viscosity, geometric variables that relate to the geometry of the problem and its scalings of lengths, and also these kinematic variables of dimensionless dynamic pressures that are applied to a system through the Euler number. And so if you can take all of these terms which represent the fluid properties, density, viscosity, the geometry, the different lengths, and the dynamic features, I guess, of the system, such as how quickly the fluid is flowing, what the pressure is that's applied to make the fluid flow, then we can combine them in some way to put them into non-dimensional variables. Then what we can do is we can derive expressions or relationships between those groups which tell us how the system works. So incredibly powerful. It works, it's worked for 3 centuries in terms of defining behaviors, allows you to do the minimum number of experiments to be able to characterize how a system works, and most importantly then to upscale it to be able to say that if you have a 50th scale model of an aircraft, then you can apply it to the prototype and figure out exactly what the forces would be on that would make it fly, lift, and also act against it flying, such as drag as it goes through the air. So there's a formula or a recipe, if you like, that allows us to do that. And that recipe is called Buckingham Pi. Groups often go into some very specific categories, which are the ratios of inertial to viscous forces, Reynolds number, the ratios of inertial to gravity forces, as in the Froude number, and the ratios of pressure to inertial forces in the Euler number. So this really is our the behavior of the jet engine hitting the truck and rolling it off the dock at SFO. The pressure that's applied on the truck is by killing the momentum of the fluid at the bottom. So they're all ratios of important forces, and we went through that. The recipe that we use to be able to group them into these terms is called Buckingham Pi. You can probably guess that you might have a question on that. I think it's been a standard for the last X years. Importantly, if you define the number of variables that describe your problem, and also if you can define the numbers of mass, length, and time which are included in these variables. If it's all 3, then it's 3. If there are only 2 of these present, then it's 2. But the difference between these defines the number of dimensionless groups that you end up with. And the importance of this is that you can relate not friction factor, but in this case, if you have 2 pi groups, you can relate them to each other. Not necessarily by a constant of multiplication. Could be reciprocal, could be something that changes non-linearly. But if you only have 2 pi groups, then you'd expect that if you plot these variables for an experiment on 2 axes, then you end up with some relationship. If you had an extra variable that would change the length to width of your system, then you could imagine that this might be for a third variable. I guess for pipe flow, they might be for different lengths over diameters equal to, I'm just making up a number here, 10. And this might be equal to 1. So clearly, if you have other terms here, then these would be the third pi group. And so if you have 2 pi groups, it'll end up looking like this. If you have If you have 3 pi groups, it'll end up looking like this. And so that's just the meaning of this. Of course, so I draw a line. It could actually be a point. So, but I guess no, it wouldn't. It'd be a line. No, could be a point, I guess.
Question.
Yeah, shout.
So you have more than 5 variables.
Yes.
Okay. And so the number of groups that you find, that's how many pi.
If I added something else here, like
So you had and
what am I going to add? Gravity, I guess, right? If I added gravity to this, I'd have 1, 2, 3, 4, 5, 6. I would have I have mass, length, and time. So this is kilograms per length, and so mass and length are in there. This has time in it, Pascal seconds. It's also this. So I have 3 of these. So this would be 6, 3, and 3. So it would look like this. If I had something else extra, which was length over diameter, then this would be 7, 3, and it would be 4. And I'm not sure how you represent 4 on a graph so easily, but okay.
wait, so that's the right hand side.
Say again.
So that one's on the right hand side. That's when you have 3.
This is 3. Yeah. So it means you have 1 and 2, and then you have multiple lines which represent different values of pi 3.
So what's that one over there? Is
It
that
would.
also 3?
This one here?
Yeah.
Yes. Yes. Yes, it is. So this is in here somewhere. Let's skip through. This is this. So if you have 2 pi terms, it's going to be a single curve. Could be all over the place, who knows where it's going to go, but you have a single curve. It means that uniquely for a value of pi 2, you have a unique value of pi 1. And typically, these have been for us Reynolds number, and this has been kind of an Euler number for the pipe flow problem. Euler number, I think, is equivalent to 1 over friction factor, kind of. Not exactly, but. And this would be for 3 groups. So this could, for instance, be... so I guess intrinsically, our pipe flow problems are 3 pi terms. We have Reynolds number, we have a friction factor, which is dimensionless, and what else do we have? These are length over diameter, right? No, sorry, they're roughness, right? And so our graph really looks like this. So this is Reynolds number, this is friction factor, which is kind of which would be our pi 2, pi 3, pi 1 rather, and this is pi 3. Okay? Yeah, shout.
Does it matter if it's pi 1 or pi 2 on your y-axis?
No.
Your axis, say like block.
Yeah, it could be either. Could switch them. So yeah, so it's a choice. What isn't a choice for an exam to make it easy to grade is to define how to use Buckingham Pi, because otherwise you can get different results out of it. And so Buckingham Pi is more art than science. The science is that you can do this and you end up with some groups, but then choosing how you use those groups, if you use different variables, is different. So typically you would be told, I'm not going to go through the recipe here. So typically you'd be told which ones are your repeating variables, which are the 3 for mass, length, and time that you choose. So density, viscosity, and velocity, I don't know, as the repeating variables. And then the dependent variable would be the one that would change from each time you do it. And so you'd be told to take as repeating variables. And so here you see as step 3, if you recall, this was the pipe flow problem. So we have, this is pressure over length. This is delta P over L. So this isn't just pressure drop, it's equal to this. So this is 1, 2, 3, 4, 5. Mass, length, and time are all represented, so just as before, we'd have 2 pi groups. You're told that you have to take these as repeating variables: diameter, velocity, and density. So diameter, velocity, and density. And so the remaining 2 variables that you have to choose as dependent variables are each of these. So we're going to do Buckingham Pi 2 times, once with this as the other variable, and once with this as the other variable. That's all. Okay? And so it's this recipe that we've used. The basic idea is that we want to take the repeating variables, which we said are diameter, velocity, and density. We add to it one of the dependent variables, either pressure drop with length over viscosity. Actually, we'll do both, but the first one will be pressure drop. And what we want to be able to do is to be able to take the units of this, the exponents that multiply by the units, so that when we take this as a unit of 1 in our pi group, we figure out what we have to multiply the diameter by to be able to make sure that it has no dimensions. So we want to get a group out of all 4 of these variables so that the dimensions of that group have to be 0 mass dimensions, 0 length dimensions, 0 time dimensions. And so that's what we're doing. That's what this little simultaneous solution is. We want to multiply this by 1. So if you like, we're multiplying this by an exponent of 1. D times A, V times to the exponent B, and density to the exponent C. So we figure out what the units are for each of these. Length for diameter, velocity is length over time, and density is mass over volume. And this is pressure. We've talked about how you get the units. So come in prepared, know what the units of pressure are, know what the units of viscosity are. Those are the only difficult ones, right? In terms of mass, length, and time. You know viscosity is Pascal seconds, but then you have to do the conversion to figure out what mass, length, and time is. And then we want the exponents for m to be equal to 0, this one here. So the right-hand side has to be 0. So 1 times m, no m's here, no m's here, c times this. So we have this expression. We go through it for L. We want L to be 0, which is this term here. And we have minus 2 here. We have plus A here. We have plus B here. And we have minus 3C here. And then we do it for time, which we also want to be equal to 0. 0 in this place. And so time is here as minus 2. No times here, so this would be, if you want to put in the zeros, you can. But perhaps it's easier to leave them out. Time is here as minus b. No time in this one. No pun intended, or no funny. And then we look at the easiest ones. This has to be that c is equal to minus 1. If we know what c is, well, can't do it quite yet. We know from this that b has to be equal to minus 2. And if we now know what c and b are, then we can figure out what a is. If we know what a is, then we can substitute that back into this. For a is equal to 1. B, bless you, b is equal to minus 2. And c is equal to minus 1. And so the dependent variable is always going to be a factor of 1, right? So it's always going to be unadulterated, if you like. So this variable is going to be delta PL times d over v squared and over rho. So if we also note that the delta PL here is remember that delta PL is equal to the change in pressure along the pipe over the length of the pipe. Then if we substitute this in here, we end up with delta P right. So this is our pi group. Happens to be a combination of 2 pi groups. We don't really care. This is the Euler number, and this is just a dimensional ratio. So for instance, if we had done it with including the value of L here, we'd end up with 3 pi groups. In this case, we only have 2 pi groups because this pi group automatically includes 2 non-dimensional numbers. So and they always have to be together. That's the supposition. Okay. And then we do it again. So now we've done this once with pressure as the free term. We said that the other free term we have is viscosity. So all we're going to do is going to use the same dependent variables now, but with viscosity. And so we know that when we do that, all of these terms here, they're not going to change. Right? These terms here aren't going to change in any way. Forget these exponents we just calculated. The a's, b's, and c's can change, but this equation here will not change. So if you look at this, these are the 3 terms we had before. They can be identical to the case we had before. Actually, they have to, this matrix here, these terms all have to look exactly the same as this. 0, 0, C. Let me make it smaller. 0, 0, C is 0, 0, C. AB minus 3C, AB minus 3C. So all that's going to change is that we have this term here to the power 1. And so we're just going to substitute, if you like, these 3 terms here for new ones here. So mass is plus 1, length is minus 1, and time is minus 1. And so you don't have to recast these separate ones. If you didn't realize that now. And then we go through the same thing. We figure out simultaneously by solving this what the A's, B's, and C's are. Here we know that C has to be equal to -1. Here we know that B has to be equal to -1. And if we know C and B, then we solve for A. Go back in, we substitute for the values of A, B, and C, and don't know if it's expression, Bob's your uncle, as the expression goes. Don't know where that comes from. This is Reynolds number. Actually, it's 1 over Reynolds number, right? And so not unusually, we get 2 terms out of it that are Reynolds numbers. Not always Reynolds number and Euler number. Sometimes they're different combinations. We've talked about 3 different terms. And we've talked about the fact that Reynolds number is what indexes behavior. And so typically Reynolds number turns up in it. But the other ones are typically either Euler number, which give the dynamic forces on the structure, and also Froude number, which also give the dynamic forces on the structure.
So how do you know which are the dependent and repeating variables?
In an exam you're told, because it makes it easy to grade. Otherwise it's impossible. And otherwise it's skill. I guess the word is that you're supposed to take, for non-exam related questions, you're supposed to choose the repeating variables that include all of mass, length, and time when they're combined. They have to include all those groups to make it easy. But yeah, but you'd be told this stuff. Okay, questions? Yep, shout.
So the K minus R term that gave us 3, that's what told us we need 3 repeating variables. Is that how that goes?
Yeah, in this particular question, it would have told us we needed 2 repeating variables because we had 5 minus 3 in this one. This is it. And we only need 2 pi terms. If for instance, this had been change in pressure, and we also needed a length of the pipe, then we'd have ended up with 3 pi terms. Because we'd have, well, you can see what they are, right? We'd have ended up with an Euler number, and we'd have ended up with a length over diameter.
The 2 stands for dependent variables.
What 2?
K minus R.
The 2 stands for 2 non-dimensional pi terms. This is pi terms, which may be pi 1.
We can't use like rho where we had viscosity in the last one because it's repeating variable.
You don't need to use it, no. If it's defined as a repeating variable, then you have to use those. I don't want to. I'm messing this up. The repeating variables are the ones that you're told to use. You cannot. So you have 3 repeating variables always, and you'll have 2 remaining dependent variables, and you have to use each of those dependent variables in turn. Okay. We've talked about what this means in terms of 2 pi groups versus 3 pi groups. We also, we're running short of time. So in any solution, you have to have a model that looks like a real model. So we have to have geometric similitude. We want the flow regime to look like the real flow regime at that particular velocity, which usually means that the Reynolds numbers in the model and the Reynolds numbers in the prototype are the same. And we usually want dynamic similitude, and for us that means either the Euler number in the model is equal to the Euler number in the prototype, or the Froude number. And it allows us to then get something out of the system. Right? So geometric similitude, model, the plane has to look like a plane, just shrunk down. Kinematic similitude, the velocity has to be the right velocity, so that when you look at, for instance, flow past this cylinder, it's either at very low Reynolds numbers, when you have it hugging the cylinder, or you have it at very high Reynolds numbers when it's shedding vortices off the top. and going downstream. So this is Reynolds number equivalency. And so if you want to get the right flow regime, you have to do it the right Reynolds number. And we know what Reynolds numbers are. A couple of examples, I won't go through those. I think we did that in class, so you can look it up. So any question on similitude? So that's 2/3 of the test. So I know you're smart and you'll use your time where it makes sense, but 2/3 of the questions are dynamic dimensional analysis. 1/3 is energy equation pipe flow. Pipe flow, what do we know? Well, we've seen this before. This is our Bernoulli equation. I guess the only new thing is that now we've said that the minor losses are this. And in Josh's question, we made the point that minor losses are what they are because we assume they're turbulent, and so they're typically given by a single value of a friction factor or a loss coefficient. It's much easier to mark things when you're given a single value for friction factor. In your test, you'll get a Moody chart, so that'll tell you something as well on what the questions might be. The major losses are this. I guess these. We haven't done this. You're not responsible for this. And we can look at a Moody chart. So yeah. So you know that the head loss for the major ones are equal to a friction factor, length of pipe, diameter of pipe, velocity in the pipe over 2g. And to get the friction factor, we know that for pipes of any section, I suppose, that they have some diameter, I guess, hydraulic diameter. They have some relative roughness. Again, a hydraulic diameter. And what is hydraulic diameter? It's 4 times area over perimeter, I think, right? Should be here somewhere. Yeah. Okay. And we know typically for pipe flow equations we use Moody chart. I've already drawn this once today. But you know, I mean, the basic idea of the Moody chart is it gives you a friction factor from large to small as a function of Reynolds number, which is a function of what? Velocity, density, and hydraulic diameter over viscosity. So inertial term over viscous losses. And yeah, ciao.
Is it possible to have minor and major losses in the same
Network? Yeah. Yeah. And you just sum them up.
How can you tell when you have major?
Because you're told that the loss coefficient is KL and that there's friction in the pipe.
Because I saw a problem where it gave you KL, but you didn't. There were both. You had to use
The pump problem we just did? Yeah, sure. So the pump problem we just did came before we actually talked about, it was in chapter 8, I think. And so it was before we started talking about losses in pipes. But you'll be told. It'll be clear to you that you need to use both if you need to use both. Don't worry. I will be explicit, just because it makes grading it a disaster, frankly. So yeah, so you know. And I guess the regimes, we've said this before, these lines are horizontal, right, because they're a function of relative roughness. So this is rough. This is smoother. You remember there's a line here that goes down as a smooth pipe. So this is, we can look at the actual Moody chart, but it's easier to mark these out. and this is equal to some coefficient over Reynolds number. For circular pipe, it's 64, etc. So, but anyway, so there's a Moody chart. So what are the keys here? Cutting you a break. Well, for instance, if something is horizontal, then you know that the elevations are going to cancel. If it goes in at the same cross-sectional area that it comes out at, then by definition, the upstream and downstream velocities have to be the same. If there's not much pressure loss on a pipe, then the pressure loss, P1 minus P2, is the pressure drop that you have to drive across the system. And so certainly if I skip through to the end, this example that we did, which you can check out on, did exactly that. What's the pressure loss, head loss in the system if you're pushing water along a duct or air along a duct? If you look at flow along the duct, by definition, the cross-sectional area upstream, the cross-sectional area downstream are the same, so the velocity upstream, velocity downstream have to be equivalent to each other. So the velocity that you use in the Moody chart, in the Reynolds number, has to be the velocity in the pipe. And so if you know the Reynolds number, then you can figure that out. We did some questions with what we call type 1 questions. Velocity is prescribed. If velocity is prescribed, it's a snap, kind of a snap, because all of a sudden you typically know where you are in the Reynolds number space. If you know where you are in Reynolds number, you know you're either here, or you know, much easier, you're either here, if you know the roughness, or if it's a smooth pipe, you know you're here. And therefore you can get your friction factor in one step. And so that's why it's the type 1 questions. So I've said there is a type 1 question on it. So energy equation, Moody chart, pipe flow, losses, you need to know that. And dimensional analysis, you need to know that. So in terms of what we're dealing with. So that's the kind of outline for the Moody chart. This is what a real Moody chart is. There is a Moody chart on your script. So you don't need to bring one. You know how to interpret it. So again, the things that we talked about, Reynolds number is absolutely defined if you know the velocity. Know these regions of laminar, turbulent, it's not quite a straight line, is it? And their implications. The implications is that if you're fully turbulent, this friction factor is absolutely horizontal, and therefore if you know the Reynolds number, you have a single value for it. If you know you're a smooth pipe and you know the Reynolds number, you know that you have a single value for this term as well. And if you know that you're laminar, then it's a function of Reynolds number anyway, and you can get it from this. This curve here is just equal to C over RE. And so that's it. I'm not sure, we kind of rushed through some other things, but yeah. So you know about what to use for hydraulic radius, hydraulic diameter rather, and include it in the Reynolds number, and include it in the relative roughness. So if it's non-circular pipe, then you need to use a relative roughness that includes a hydraulic diameter. If you use the loss term, it includes a hydraulic diameter. And I guess Reynolds number also is equal to velocity, density, a length term over viscosity, which is a hydraulic diameter. So these all work for non-circular section conduits. Example, yeah. So just to allay your fears, and this is about as good a summary as you get of all of this, right? This is exactly what you need to do. The only thing that's not included on here, which you might need, is the statement that is that. Otherwise, this basic little panel here includes everything you need to deal with for pipe flow questions. Okay. Any final questions? So, I will repeat it. So 2 questions. 1 2-part question on dimensional analysis, almost guaranteed Buckingham Pi. Know how to use it, know how to interpret it in terms of what 2 pi groups are, 3 pi groups are, what they'd look like on a graph, what the typical dimensional parameters would be, Reynolds number for kinematic scaling, and either Froude number or Euler number for dynamic scaling. Know how you can use those to switch between model and prototype just by looking at the same Reynolds number, for example. So that's dimensional analysis. Know how to do the recipe, because you'll need to do that. And pipe flow. Given on this panel here, know how to use these equations. This is equal to 1, typically. And know how to, if it's on the same elevation, then Z1 and Z2 are the same. If the pipe doesn't change diameter, then these drop out, and all you have is pressure driving flow. Power you have to put into the system by a pump, bless you, and any head losses that you might have by flowing along a big length of pipe and or going through fittings. And if you have to do that, it'll be pretty explicit to you what those numbers would be. Either pull them from a Moody chart or pull them out of a friction factor, K sub L rather, is given to you. So that's it. Okay? Yes?
What is phi?
Where? Phi? Oh, function of. Yeah, I guess, yeah. So friction factor is a function of. I mean, function of is usually an F, right? So, but it's ambiguous with friction factor. Phi means function of. Well, you might have to. Yeah, you might have to. Yeah. Yeah. So know what the typical pi terms are that we've used. We've used 3 of them. We've talked about 3 of them. Know what they mean in terms of ratios of forces as well, maybe. Okay. Great. So, well, happy hunting on Thursday. I think everything's worked out. Lubisha, as I understand, has rescheduled the thermo. The PNG, is it 405, 406, or whatever it is I realized the same day and before, but take it early and clear your head so you're ready for this. Same protocols as before, 8 o'clock onwards until midnight. I presume you can stay longer than that if you can persuade people. I think it's about the same length as the other tests. I think this is more formulaic and more straightforward. You really know what to look at for this, from what we've said today, I think, and from looking at past exams. So you can prepare yourself well for this. So I expect you to ace this, and then we're all looking pretty for the final. So no class Thursday, no class Friday. Nick will be in touch with presentations for next week, week 13, and then it's Turkey week. And I'm pretty sure in advance we won't meet on hunting season the first day of after Thanksgiving, on the first Monday. But we will meet for the rest of that 2 week. And then it's the end of the semester. The end of your ordeal will be nigh, and you'll get a break at December. Christmas, Kwanzaa, Hanukkah, Eid, whatever you celebrate, you'll get to take off your time. If I didn't miss anything out. Must be Buddhist. I'm not sure what the Buddhist festivals are. All right? Good luck. I expect to see great things from you all.